Hello, so we'll have today a second presentation on operator algebras. This time it's going to be basic spectral theory, so we'll get a bit into the tools which can be developed in order to study these algebras. So what's the idea is very simple. So these operators are basically infinite matrices, so we'll look for analogs of the eigenvalues, try to develop eigenvalue theory for them. So let's find this presentation first. Here we go. So basic spectral theory. We learned some very basic things. So we'll use the framework that we found last time. So we'll call this time abstract system algebra, complex algebra with a norm, making it Banach algebra, and an involution such that this key formula is satisfied. A star in norm is a to the square in norm. So what's the point of this? So we know that B of H is a system algebra. That was the main thing that we put last time. We'll solve the norm closed star subalgebras of B of H are system algebras in this sense. And we'll actually see later that any abstract system algebra actually appears as a norm closed star subalgebra of B of H. So it's the same thing, abstract system algebra in this sense and concrete system algebra in the sense that it's a subalgebra of B of H norm closed. However, it's better to do it in this abstract way because we don't lose anything, right? All these covers, all operator algebras, but we gain something because we'll see later with this definition, you can construct many examples of system algebras just with generators and relations. You have a lot of these there that you can construct in this way with generators and relations. And you cannot do that if you have a Hilbert space around. So it's better to do it like this. Now, what we want to do is to speak about eigenvalues. So let's define the spectrum of an element to be the complex numbers lambda such that a minus lambda is not invertible. Lambda means, of course, lambda times 1. And for the usual matrices, you obtain the eigenvalues because NV is lambda V is the same as n minus lambda to be not invertible. There is one subtlety, however, that is that for the matrices, you not compute the eigenvalues with multiplicities. Here is just a set, is the set of eigenvalues without multiplicities. So we study this set. The first thing that you can say is that it's a compact subset of C. It's containing the disk centered at 0 of radius norm of A. Why is this true? So first of all, my first claim is that the spectrum of a norm 1 element is in the unit disk. Why? If you just use this formula, right? You can invert 1 minus A like this with a series, and you're done. Now by dilation, of course, this will give you item 2 here in the disk. And also it proves that the invertibles are open. So now if you look at the definition of the spectrum here, it's basically a matter of applying of continuous function to an open set to get something open. So complementary is closed. So finally the spectrum is closed. It's also bounded, we know it, so it's compact. We're done with this. Now, what's less trivial now is to prove that the spectrum is non-empty, and that you have at least one eigenvalue. And this is really tricky. So we do it by contradiction. So now let's pick an arbitrary linear form and apply it to the inverse of lambda minus A. Okay, I use here the fact that the spectrum is empty. These things exist. This inverse is for any lambda. So now f is of course differentiable because the inverse is differentiable. It's the same formula as in the classical case, classical calculus. So it's holomorphic. And now the point is that then inequality will prove that f, so it's holomorphic, and it's going to decrease at infinity to 0. So by uv it's going to be 0, and that would be a contradiction. So now let's look at the main estimate. So I assume that lambda is big. And then in order to invert this guy here, I use the formula before, okay? So I need to rescale A by lambda as to B of norm less than 1 when lambda is big. So I do just this, I factor by lambda. So I get this, I apply my formula of inversion. Another point is that the norm gets inside all the terms here. So this is smaller than 1 plus norm of A over value, absolute value of lambda, and so on. And what we get here when you put the norm inside is the usual geometric series. And you can sum it and you get this, you see? So now that we have our inequality, of course, when omni is big, this goes to 0, by will it's 0. So this thing must be 0, and it cannot because it's an inverse contradiction. So the spectrum is non-empty, compact, and containing the disk. That's what we know. Now, another thing is that if you take two matrices, A, B, and B have the same spectrum. The same happens here, but not necessarily on the point 0. So let's see how this goes. For the equality, well, it's enough to do it for lambda is 1 by dilation, and this follows from the following thing. If 1 minus IB is invertible, 1 minus BA is invertible too. Now for the counterexample at 0, consider the shift. I mean, L2 of 10 just shifts at right, S star shifts at left. So if you compose S and then S star is the identity, but S star and S is not the identity. You'll miss E0 here. So this means that one is invertible, S star S, but S star is not. So the spectra don't coincide at 0. Now, what can we do next? You can apply functions to elements, and that's something that you know for matrices. If you apply a function, this gets applied to the eigenvalues. In order to apply the function, we'll do it for rational functions. We need this thing Q of A to be non-zero, so F must have poles outside spectrum of A in order to formulate our thing. And if this is true, the formula is true. Sigma of F is F of sigma. So let's see how the proof goes. For polynomials, probably just decompose to factors, and product is invertible if and only if all factors are invertible, you're done. In the general case, well, that's the trick. I mean, you have a quotient of polynomials, so you take P minus lambda Q, and you see from this, you pass to this by using the thing for polynomials, and you're done. So it's a bit tricky. Now, what else can we say? Once again, analogy with matrices. So if you take a unitary, the spectrum is on the unit circle. Why you use this rational calculus with z minus 1? So see, I use the unitarity here, and I get that lambda is in the spectrum. It means that lambda minus 1 must be lambda bar. It's on the unit circle. Now, the point now is that if you have things for unitaries, you can pass to self-adjoints. Using this function here, z plus it over z minus it with t real. So z when t is real and big, f of a is well defined and it's clearly unitary. So the spectrum is in t. Now by getting back via f, again that the spectrum consists of real numbers. Now, one more thing, this is going to be more difficult. So we already know that the spectral radius, meaning the radius of the smallest disk containing the spectrum, is more than the norm. That's something that we already did. Now we'll prove that for Norman elements is exactly the norm. That's very important. So in order to do it, we fix a rho greater than the spectral radius, and then you can apply this integration formula here, quotient, you get something like this. You apply the norm, so you get exactly what you want, but the limit here. Would like to have norm of A here, and we're done. So in the self-adjoint case, of course, this is like stationary, at least for powers of 2 exponents, so you're done. In general, well, you use the fact that A star norm is A to the square norm, and you reduce to the self-adjoint case, and you're done. So spectral radius equals the norm for normal elements. That's very important. Okay, so this is was for today, and next time I'll apply all these to get some results about C-star algebras. See you soon.